In this video, we're going to continue our discussion of lines, their equations, how to graph them, all that fun stuff. But we're going to focus primarily on the properties of parallel and perpendicular lines, okay? And of course, what I want to recall from, say, geometry is the fact that parallel lines, by definition, at least in a Euclidean sense, parallel lines are two lines that do not intersect, okay? Do not intersect, and I've kind of illustrated that here, if you can see that there. And then perpendicular lines, of course, are two lines that, in two dimensions at least, cross at a 90-degree angle or intersect at a 90-degree angle, okay? And they're two kind of special cases that we want to be familiar with, so let's talk about them. Okay, starting with parallel lines, okay? So a quick observation over here. You'll notice that I've drawn in two lines. I call them line 1 and line 2. And just real quick, I just wanted to kind of talk about their slopes, or at least their grade or their steepness. But think about this. In a Euclidean sense, if two lines were to be parallel, that is, never intersect, it would be the case that they must have the same slope. That is, they're running away from each other, or say this top line is running away from the bottom line at the same rate that the bottom line is trying to catch up with the top line. But since they started in different places, it's just kind of an interpretation of it. You'll never be able to catch it because they're going, say, the same speed or rate, okay? So that being kind of said here, it would be reasonable to deduce that these would have to have the same rate, the same slope. So it is the case that, if you're taking notes, it is the case that, but it is the case that two lines that are parallel must have the same slope. And well, not conversely, but looking at perpendicular lines, I think it's safe to say that at least, let's start with the specific case of line 1 here. Line 1, if we talked about perpendicular lines, it would have to be the case that if line 1 is increasing, line 2 would have to be decreasing, okay? And we could talk about a specific case where one of these would be horizontal, the other one would be vertical, and you'd have zero slope and undefined slope. But the fact of the matter is this, they have to be kind of opposite in behavior. That is, slope number 1 is positive, slope number 2 will be negative. But also this, and this is the odd thing about it, we say slope number 1, given slope number 1, m1, the slope of the first line here, the slope of the second line would be the negative reciprocal of the slope of the first line. So first things first, you'll notice if one's positive, the other one will be negative. What if m1 was negative to begin with? I just want you to know that this negative sign here serves only to say that the slope of the second line must be opposite the slope of the first line. Okay, so they have to have differing signs. All right. The other thing is this. I'll ask people, I say, given a line, say it had a slope of, say, 2/3, just for the sake of argument, positive 2/3. So say it had a y-intercept of 0 and went up 2 and it went out 3. And I said, okay, so let's find a line that's actually perpendicular to this sucker right here. And they say, oh, well, what about negative 2/3? Okay, negative 2/3. Well, let's assume I went down 2 and out 3 here. You're going to notice that they don't cross at a right angle, okay? We have to be a little bit more, elaborate on this one and say that it's the negative reciprocal of the first one. So let's say not only if we said if the slope of the first line was 2/3 up 2/3, and the slope of the second line was negative 2/3, that wouldn't work. But what if we had flipped the original relationship between rise and run? What about negative but 3/2? Okay, so if we had gone down 3 and out 2, okay, and I'll even switch colors on this one here, and we had connected these two lines, and this is a by hand drawing, but we would have had perpendicular lines. So all this formula is basically stating here is that perpendicular slopes are negative reciprocals of one another. In other words, if I give you a slope and I say, hey, what's the slope of a perpendicular line? Take the original slope, flip it, and negate it. Okay, that is, if it's negative already, you make it positive. If it's positive, make it negative. We're just going to kind of play on these relationships and go through a couple of examples of how I might want to find the equation of a line passing through, say, a given point, but perpendicular or parallel to, say, some other line. Okay, so let's take a look at this first example down here. We say, okay, we would like to find the equation of a line passing through this point here, 2, 3, but we want it to be parallel to the line y equals 4 minus 2/3 x. Okay, what I'm going to start by saying is this. Recall that when you're finding the equation of a line, we're going to be using this idea or this formula called point slope formula. Okay, and the reason why, remember, we called it point slope formula is because we need a point, which we have, a point on the line, 2, 3. We also need a slope. The interesting thing about this example is that I've not necessarily given you a slope explicitly. I didn't say, hey, I want it to have this slope. I asked for a slope or a line that would be parallel to this line over here. Okay. And what do we know about parallel lines, or at least what do we know about their slopes specifically? They have to have the same rate or the same slope. So here's the thing about it. We need a point. We have a point. Okay. We have this point. X1, Y1 would be our 2, 3. So we're good on these values right here. But as far as slope goes, if it's going to be parallel to this line over here, we'll just adopt the same slope. So of course the question is, which one's the slope, the 4 or the negative 2/3? That is a negative, by the way. And it would be the negative 2/3 because that's our coefficient of x in this linear equation, okay? So I'm going to go ahead and explicitly write these. We say we got the point 2, 3, and we want a slope that is the same as the given slope of the other line that we wanted it to be parallel to. So now we'll go ahead and do a little fill in the blanks here. We say y minus y1 is equal to slope m times the quantity x minus x1, and start filling stuff in. Like, we knew we wanted a y value of 3, we wanted an x value of 2, but we also wanted this slope that's parallel to this one, so we say, okay, negative 2/3. So now all we need to do is simplify this, and you know, we tend to like to isolate y, so let's go ahead and do this. Let's distribute on the right side here. So negative 2/3 times positive x, of course, is negative 2/3 x. So there's our parallel slope already. This x is going to be stuck with this negative 2/3 attached to it. But negative 2/3 times negative 2, negative times a negative is a positive. And if I had 2 of these thirds and I doubled that, okay, then we have 4/3 now, so 4/3. So the last thing to do here is we'll add 3 to both sides. Add 3. Add 3 to the constants. So now we've got this. Y equals negative 2/3 x. Okay, and 3 plus 4/3, 3 wholes would be the same thing as 9/3. And 9/3 plus 4/3 would give us 13/3. Okay. So, you know, if we kind of imagine this here, we say this first line here was up 4, you know, 1, 2, 3, 4. And then it went down 2 and over 3. So 1, 2, and then out 3. 1, 2, 3. Right there. So here's our first line. And then we have this equation of the second line, which we found out was up 13/3. So 3 precedes into 13 4 times with another third. So it's just a shade above this line. And it would still go down 2 and over 3. So this would be a shade above this, but we'd have 2 parallel lines. Okay. So let's take a look at the case where we want perpendicular. All right. Starting with this, we say find the equation of a line passing through this point. So we want to go through 3, 0. But with the, this time we want it to be perpendicular to a line passing through 3, 4, and 5, 1. So first things first, let's go ahead and sketch these second 2 points. We got 3 up 4, or 3 up 4, and then we say we'll go out 5 and up 1. I think it's clear to say on this one that this line that we want to be perpendicular to has a negative slope. So whatever the equation of a line we're finding, it's going to pass through this point 3, 0 right here. It had better be going uphill, and we can already kind of imagine or fathom that it's going to kind of go off in this direction. I'm just kind of trying to illustrate it here. But fact of the matter is this. We're going to be using point-slope form again. We need this right here. And the good news is this. We've already got some given information. We've got the point we want it to proceed through. The only thing we seem to be lacking at this point, is a slope, okay? And this is where we're going to use this idea of the relationship of the slopes between two perpendicular lines. So go ahead and, maybe we put in the y value here. We say this is 0, and put in the x value. We say this is 3. But we need to find this, and it needs to be perpendicular to the line going through these 2 points. So first things first, we're going to need to find the slope of this second line. So slope of the second line, we say slope is rise over run, or difference in the y values over difference in the x values, or delta y over delta x. We say, okay, so 1 minus 4 on top, and there's where our negative is going to pop out. You'll see here, because 5 minus 3 on bottom is going to be positive, the top's negative. But we've got a slope of the second line being negative 3 over 2. So this is the slope of the second line. We want our line to be perpendicular to this, okay? So if this is the slope of the second line, we want the negative reciprocal of this to be the slope of the first line. So first things first, this is already negative, so if we negate a negative, the slope of the first line should be positive. And, looking at this, that makes sense, okay? But the reciprocal of this would be 2/3. So now we've got this value that we're going to go ahead and place in here. Say, let's do some simplifying. Already y minus 0 is just going to tend to y. And we say, okay, distributing this 2/3, now I've got 2/3 x minus, now this is cool, this 3 here and this 3 here will cancel out. So a positive 2/3 times a negative 3 is negative, and the 3's cancel, we have 2. So this has a y-intercept of negative 2, which seems very reasonable if you're looking at this illustration that I did by hand, by the way. And the slope would go up 2 over 3. So a lot of the stuff we've been using in the past kind of coming together here to help us find equations of lines that may be perpendicular or parallel.